How much of the Earth's surface is covered with water? Is it 50%? Is it more than 50%? Is it less than 50%? There are many different ways that you can answer this question. A simple way would be to do an internet search and find an answer that way. According to this source, approximately 71% of the Earth's surface is covered with water. Although we were able to find an answer very quickly, the issue with this approach is that it only works on questions that already have known answers. What happens when you run into a question that doesn't currently have a known answer? Learning how to perform internet searches doesn't exactly provide you with the necessary life skills to tackle more difficult questions. A more sophisticated approach would be to use probabilistic programming. Probabilistic programming provides you with a set of tools to help you explore questions that don't currently have known answers. This is incredibly valuable for anyone who may be exploring the frontier of human knowledge. So what is probabilistic programming, and how can you use it to answer the question, how much of the Earth's surface is covered with water? Well, let's find out. Welcome to Doggo.jl, where I explore the vast Julia wilderness and turn my discoveries into wholesome Julia tutorials. For this series, I'm assuming that you do not have a background in either Bayesian statistics or probabilistic programming. But I am assuming that you know the basics of how to write code using Julia. I'm also assuming that you're comfortable using Julia in both VS Code and in Pluto notebooks. For Julia, I'm using version 1.9.0. With that said, let's jump into VS Code and get started. In VS Code, create a new folder for this tutorial. In the tutorial folder, create a new Julia file. Launch the Julia REPL by using Alt-J, then Alt-O. Change the present working directory to your tutorial directory. Enter the package manager by using the closing square brackets. Activate the tutorial directory. Add the Turing package and the statsplots package. Exit the package manager by hitting backspace. In the editor, add the code to load the packages. Okay, we are now ready to begin our journey into the world of probabilistic programming. This tutorial series is inspired by the work of Richard McElreath, who is an American professor of anthropology and a director of the Max Planck Institute for Evolutionary Anthropology, which is located in Germany. I'm not sure how to pronounce his surname, but as an interesting side note, he has a Twitter post from 2019 listing over 50 different ways to pronounce his name. In his post, he states that he doesn't have a preference for how his surname is pronounced. In his lectures, he often introduces himself simply as Richard. So, in addition to being a professor and a director, he's also the author of a textbook titled Statistical Rethinking, which was originally published in 2015. He also has a YouTube channel where he has generously uploaded his lectures on statistical rethinking and made them available to the public for free. His lectures are a lot of fun, and his slides contain plenty of memes. So his lectures are Doggo approved by this meme-loving doggo. Unlike traditional statistics textbooks, written from the point of view of statisticians, he approaches statistics from the point of view of a scientist. In his textbook, he presents a version of statistics that is free of the rigors of traditional statistics in order to make it more practical and useful for real-world scientific research. He does this by combining Bayesian statistics, where probability expresses a degree of belief in an event, and probabilistic programming, which is the application of modern computers and modern programming languages for Bayesian statistics. The code that he uses in his textbook is primarily written using Stan and R, which are domain-specific languages that are pioneers in the field of probabilistic programming. Fortunately for us, several members of the Julia community have already gone through his textbook and generate Julia versions of his code using the Turing.jl package. The source code for this tutorial comes from a combination of the Turing Models.jl repository on GitHub, which has several contributors, and from the personal website of Neil Grantham. I've gone through their code and made some slight modifications for the purposes of this video. I've provided links to all of these resources in the description below. Now, before we can tackle the problem for this tutorial, we need to get a crash course on probability distributions. In the interest of time, I've prepared a Pluto notebook that shows the probability distributions that we need for this tutorial. You can find a copy of this Pluto notebook in my GitHub repository. There's a link to my GitHub repo in the description below. The first probability distribution is the normal distribution, which is the hello world of probability distributions. What you're looking at is a plot of something called a probability density function, or PDF. The shape of the PDF for the normal distribution is also referred to as a bell curve. The normal distribution takes two parameters, the mean and the standard deviation. The mean, denoted by the lowercase Greek letter mu, determines the center of the symmetric distribution. In the plot, the mean is represented by the orange vertical line. The standard deviation, denoted by the lowercase Greek letter sigma, determines how wide the distribution is spread out. In the plot, the standard deviations are represented by the two green vertical lines. The green line to the right of the mean is the positive standard deviation, and the green line to the left of the mean is the negative standard deviation. This plot shows the PDF for a normal distribution with a mean of 0 and a standard deviation of 1. The area under the curve is equal to 1. If you change the value of the mean, the distribution curve simply shifts side to side. If you change the value of the standard deviation, the distribution curve either gets tall and skinny or flat and wide. Even if the shape of the curve changes, the area under the curve will always be equal to 1. The next probability distribution is the beta distribution. The beta distribution takes two parameters, alpha and beta. When alpha and beta are both equal to 1, the shape of its PDF is flat, or uniform. The area under the curve for any PDF is 1. If you increase the value of alpha above 1 while beta is 1, then the curve shifts to the right. If you decrease the value of alpha below 1 while beta is 1, then the curve shifts to the left. If you increase the value of beta above 1 while alpha is 1, then the curve shifts to the left. If you decrease the value of beta below 1 while alpha is 1, then the curve shifts to the right. The beta distribution is a very flexible distribution, so you can adjust the values of alpha and/or beta to fit many different shapes. The last distribution is the binomial distribution. Both the normal distribution and the beta distribution are examples of continuous probability distributions, meaning that the data can be any value within a certain range. The binomial distribution is an example of a discrete probability distribution, meaning that the data can only be certain values. The binomial distribution takes two parameters, the number of trials, or n, and the probability of success, or p. Each trial answers a true-false question, like yes-no or heads-tails. For this distribution, each trial is assumed to be independent of each other, and the probability of success for each trial is identically distributed. Discrete probability distributions are visualized using a probability mass function, as opposed to a probability density function. If there's only one trial, then this special case is known as a Bernoulli trial. Here, 0 means failure, and 1 means success. The probability of failure is 1 minus the probability of success. So as you change the probability of success, the probability of failure changes accordingly. As you increase the number of trials, the probability mass function begins to spread out and begins to resemble a probability density function, but using only discrete values. By changing the values of n and p, you can come up with a lot of different distributions. Okay, now that we're familiar with a few distribution curves, let's try to tackle the actual problem. Take a globe and toss it in the air. When you catch the globe, place your finger randomly on the surface. And then, record if your finger is pointing to water or to land. If you toss the globe 9 times, how many times will your finger point to water? The traditional approach to solving this problem is to start with the inputs, and then run the inputs through a model. The model will then return the output. So in this example, the inputs are n and p, where n is the number of tosses, and p is the percentage of water that is covering the surface of the Earth. So if we toss the globe 9 times, then n is 9. For the value of p, let's use 0.71, which is the value that we found using an internet search. For our model, let's define a function of n and p that returns an integer. The output is the answer to the question, if you toss a globe 9 times, how many times will your finger point to water? In order to find this output, all we need to do is call the function. So according to this traditional approach to problem solving, if you toss a globe 9 times and randomly point to the surface, your finger should point to water 6 out of the 9 times. As long as you know the value of p, or the percentage of water that's covering the surface of the Earth, then it's easy to solve this problem. But what happens if you don't know the value of p? If you only know that your finger pointed to water 6 out of the 9 times when you tossed the globe, is it possible to back into the value of p? If you try to work backwards, then the value of p is 67%, and not 71%. But that's not all. There are several different values of p that will give you the same output. For example, using 0.62 or 0.72 will also give you the same output. If you try to work backwards, then you'll find that there are an infinite number of possible values of p that will give you the same output. So which is the so-called correct answer? This is where Bayesian statistics comes in. In Bayesian statistics, the answer to the question is not a single number. A Bayesian solution to a problem is a probability distribution around a range of possible values. Let's take a look at how to approach problems the Bayesian way. The workflow for solving a problem using Bayesian statistics and probabilistic programming is to start with the output and then run that output through a model. The model will then return the input. In this example, the outputs are the observations from our globe tossing experiment. Let's say that we tossed the globe 9 times and our finger pointed to water 6 out of the 9 times. Now, we need to take these observations and feed them into a model. Because we're looking for a probability distribution and not a single number, our model needs to speak the language of probabilities. The design of our model comes from Bayes' theorem, which states that the posterior is equal to the prior times the likelihood. We'll cover this equation in more detail in the next tutorial. For now, all you need to know is that we need to inform Turing about the probability distributions for the prior and the likelihood in the model definition. When defining a model in Turing, we need to use the @model macro. In this model, the unknown parameter that we're trying to solve for is %_water. We know the values of tosses and water from our experimental observations. The tilde character is used in statistics and probability theory to mean is distributed as. So the variable named %_water is distributed as a beta distribution. And the variable named water is distributed as a binomial distribution. We saw both the beta distribution and the binomial distribution in the Pluto notebook. We'll go into more details about the terminology and syntax in the next tutorial. Now that we have our model, we need to solve it in order to find the input. Unfortunately, in many cases, we cannot solve a Bayesian model directly. Instead, we need to use a random sampling process in order to infer the distribution of the input parameter. In statistics, the term inference means that we take samples from a larger population. And from those limited samples, we can infer the characteristics of the entire population. In Bayesian statistics, this inference process will result in an approximation of the posterior distribution of the input parameter. In Turing, taking samples is accomplished by the appropriately named sample function. The sample function takes 3 arguments: a model, a sampler, and the number of samples. The sampler is an algorithm that defines how your computer takes samples from the model. The sampler that we're using in this example is named NUTS, which stands for the No U-Turn Sampler. We'll learn more about this particular sampler and about the various other samplers available in the Turing.jl package later in the series. In this example, we're taking or drawing 1,000 samples. There's nothing special about this number of samples, so you can play around with this value to see if it makes any difference in your results. The sample function returns something called a chain. The first time you call the sample function, it may take a few minutes, depending on how many samples that your sampler is drawing and on the speed of your computer. It will be much faster the next time you call the sample function. While you're waiting, maximize the REPL, so you'll be able to see the results. This may look intimidating, but this is where all of the magic is. There's a lot of good information in this printout, but for now, let's take a look at the summary statistics table under the column labeled Mean. According to this output, the mean value of the percent of water on the Earth's surface is around 62%. Also, notice that the standard deviation is around 14%. So the percent of water could be anywhere from roughly 50% to roughly 80% if the true value is within one standard deviation of the mean. If you look at the quantiles table, you can see that the percent of water ranges from the 30s at the low end up to the 80s at the high end. Note that the samples are drawn randomly, so your results will look different. In VS Code, if you'd like to see the details behind the summary statistics, you can click on the Julia logo icon along the left-hand side. In the Workspace panel, look for the variable named chain. If you hover your mouse over chain, you should see a data table icon appear on the right-hand side of that line. If you click on that icon, VS Code will bring up a table of the data. Each row of this table is an individual sample. There's a lot of information in this table, but the column that we're interested in is the %_water column. It's difficult to get a sense of what's going on just by looking at all of these numbers, so let's take a look at some visualizations. The Turing.jl package uses the statsplots package for its default plots, so you can use the plot function with a variable named chain to see some standard Turing diagnostic plots. The plot on the left is called a trace plot. The trace plot shows the %_water values for the 1,000 samples that the sampler algorithm selected and kept from our model. The reason the x-axis goes from 500 to 1500 is because Turing discarded the first 500 iterations from the sampling process. These first 500 iterations are called warm-up iterations, or the quote-unquote burn-in. The plot on the right is the PDF for the approximation of the posterior distribution of the input parameter. In order to see this better, let's create a separate plot just showing this density plot. What you're looking at is the Bayesian statistics answer to the question, what input generated the output that I observed? In this case, we can interpret this as answering the question, how much of the Earth's surface is covered with water? As you can see, it's not a single number. Instead, the answer is a distribution around a range of potential answers, showing the degree of belief for each potential answer. If you're new to Bayesian statistics, it may take some time to get used to, since you may have to unlearn many things that you may have been taught in school. You'll need to get comfortable looking at problems backwards, starting from the output and solving for the input. You'll also need to get comfortable starting to look at the world through the lens of probability distributions. Bayesian statistics is not a different way to solve the same problem. You're actually solving a different problem. A problem that may not be solvable using conventional tools. But Bayesian statistics and probabilistic programming provide you with a set of tools to solve these different and previously unsolvable problems. I know that we covered a lot today, so let's break here and highlight some of the key takeaways. Unlike in classical statistics, in Bayesian statistics, probability expresses a degree of belief in an event. Probabilistic programming is the application of modern computers and modern programming languages for Bayesian statistics. Turing.jl is a software package written in Julia for probabilistic programming. Regardless of which language you decide to use, probabilistic programming provides you with a set of tools that can help shed light on questions that do not currently have known answers. This is accomplished by flipping the traditional problem-solving workflow around, so you can start with your observations from your experiments and back into the inputs that are generating your observations. In addition, these tools can often work in a resource-constrained world, so you don't necessarily need a lot of data. This makes it a practical choice for many who are interested in the discovery process. There's so much more for us to explore on our probabilistic programming journey, so stay tuned for the next exciting episode. If you made it this far, congratulations! If you enjoyed this video and you feel like you learned something new, then please consider liking, commenting, sharing, and subscribing. If you'd like to support the educational work that I'm doing, then please consider using the Super Thanks button. For ongoing support, please consider joining and becoming a channel member. Channel members get ad-free, early access to all of my new videos. Thanks for watching, and good luck on your Julia journey.